All right. Good afternoon, everybody. So today's lecture is not a technical lecture, but it's more of a, I'm going to tell you a little bit about stuff that we don't cover in this course, because in modern game development, there's a lot that needs to happen. And so the stakes can be very high in modern game development, right? So you may have heard of the recent Sony debacle with Concord. So Concord was a video game that was 8 years in development. No one knows exactly how much money was spent, but it's estimated somewhere between $50 and $200 million were spent developing this game. It came out 2 weeks ago. It's going away. Sony's officially canned it. They're handing out refunds as we speak. It was a complete failure. I have no idea what's going to happen to the people who were responsible for this game. Like, can you imagine being the manager behind this game and trying to get a job? I was the guy, or I was the person, not necessarily guy, I was the person responsible for Concord. If you need to throw away 8 years of time and $50 million, I'm your person. I don't know what they're going to do. It's crazy. So the stakes are very high. Now that's not true, that's not universally true, right? So small game development teams still exist. It's still possible for individual developers to produce very successful games. If you've heard of Inscription, that was a game that came out, I think, in 2022. It's written by a former Queen's student. It wasn't just the most highly rated indie game of 2022. It was one of the most highly rated games of 2022. So it is possible to build games, modern games, with small teams. It's somewhat unusual. Many of the games that you hear about in the media, or perhaps play, are these large, splashy AAA games. They're developed by literally hundreds of people. And they use all sorts and sorts of tools. So the teams are broken down into many different groups. All the different groups are responsible for different things. It's these different things that I'm going to hopefully tell you about today. And not even all of them, it's just some of them. All right, so in modern game development uses very highly specialized tool chains. Now it's nice, a lot of these tools are free for use for students. Or for individual people. So you can get your hands on, for example, Adobe's 3D Painter or something like that for free for personal use. However, many of the other tools that I'm going to show you today are extremely expensive and highly specialized. And so these tools fall under the name digital content creation tools. There's lots of them. Right? So for example, if you know what a texture is, or if you don't know what a texture is, don't worry about it. I'm going to explain what it is in just a second. Right? Texturing tools, 3D Painter, Photoshop, and a whole host of other texturing tools are used by artists to create what are called textures. Your 3D models, someone has to make those 3D models somehow. Right? There's all sorts of 3D modeling software available now. Blender is a commonly used open source 3D modeler. Maya, 3D Studio Max, Rhino, the list goes on and on and on and on. There's lots and lots of professional caliber tools for 3D modeling. The 3D modeling is interesting. So many of the modeling tools actually grew out of the engineering modeling tools. So engineering has been using these 3D modeling tools for quite a bit longer than, I guess, entertainment. So movies, games, etc. So the engineers are used to having these tools around. And they've been around a long time now. I'm trying to remember back when I started. So I guess in 1990, I actually had a job over in the physics department, working with one of the professors there, and we were using some two-dimensional modeling software to solve some engineering problems. The tools have come a long way since. So back then, you'd fire up your tool, you'd do some work, and you would save like every 2 minutes, because if you didn't, inevitably the tool would crash and you would lose all your work. They've come a long way since then. Audio is a big part of all modern video, not all, many modern video games. And some of them, it's the most important part. So there's all sorts of audio modeling tools. And then terrain generation falls under, I guess, the 3D model generation. Many games, especially those involving an open world sort of game, you have to generate terrain, right? The land, sky, and other geographic features in your game world, right? Generating these with the traditional 3D modeling tools is suboptimal, to say the least. So there are specialized tools which will actually generate terrain for you. Many games have quests, so especially role-playing games, right? Designing the quest in a way so that they don't break or can't be broken by the player is difficult. And so there's a whole host of quest development tools for you. Dialogue and quest development tools. And finally, if your game involves lots and lots and lots of things moving around, typically people like non-playing characters, you might consider doing some sort of crowd simulation. So I'm going to show you an example of this thing called mass motion in just a second. All right, so typically a game starts at the beginning. No one starts writing code. They start to build the digital assets in the game, and that all starts with typically concept art. So one or more artists are hired to sketch to sketch the items in the objects that will be in the world and the world itself. Right? And so I guess just very recently, Black Myth Wukong came out. So it's a game from a Chinese developer. 40 million, 50 million sales so far. Lots in a very short amount of time. If you click that link there, which I'm going to do, that'll take you to a video that shows you some of the concept art. I'm not going to play this whole video. But you can see, oh, sorry, here we go. Right? That's not a scene from the 3D world of the game. Right? That's this case, it's a digital image created by a digital artist that shows some of the elements that might be in this particular part of the world. Right? And so an artist will come along, they'll sketch out they'll sketch out the concept art for the game, and then it's up to a different group of people to actually build the assets that are used to produce this sort of to produce a picture of this in the 3D world, right? And so you can see this video just goes through some of the very beautiful art, concept art that was used in the development of this game, right? And so, can any of you actually do this sort of stuff? Does anybody here actually do this sort of digital, sort of graphic design? Anybody? Yeah, I can't do it. I have no idea. You go to Sheridan College for like 4 years to learn how to do this stuff. Yes?
Are the people who build the assets also artists?
Yes, there's so many artists involved. With some of the videos, you're going to be blown away by what's involved in making a modern game, right? Right? And even this is just the concept art. No one's selling this. Well, I guess if you buy the deluxe edition, you can get the concept art. But no one's selling this stuff, right? This is just part of the initial development of the game. Right? All right, there's a part 2 to this if you want to see well, let's take a look at part 2. Part 2 is, so you can see some of the character art. Right? And so this is the main character in the game. I forget its name. Comes from a very famous Chinese legend. And so there's the concept art that has been reduced. Right? It's all two-dimensional. It's not the three-dimensional models or assets that are going to be eventually created. Right? In the background, you can see the actual 3D art that has been created, this is what you actually see in-game. Right? And you can see that the in-game imagery is amazing. So what you can do in a modern video game, running at 30 or 60 frames per second, is incredible. Right? And if you're interested, you can just play that video and see what other concept art was created for this game. This is the other nice thing about modern game developments is that they hire somebody to develop a bunch of promotional videos for the games. So you can find the making of videos for all sorts of things. And it's actually, I'm going to show you some, and they're really very interesting. So once you start out with the concept art, or once you've got the concept art settled on, someone now has to go and bring that concept art to life. So in a 3D game, typically that means producing the three-dimensional assets that go into the game. Right? Notice there's a whole bunch of links here, so we're going to watch some videos today. This was actually a very nice lecture to put together. And so this is Rhino. So this is one of the 3D modeling. This is an example of 3D modeling software that you can use, and you can see. Oh, stop there for a second. Right, and so in most of the 3D video games, the assets, right, the three-dimensional models, they're just a bunch of triangles, right? And that's all that they are, right? And so the trick is how the heck do you actually make these 3D models, right? And so this three-dimensional modeling software helps you do that. Rhino is an example of a piece of software that uses something called NURBS, non-uniform rational B-spline. That's just a mathematical, those are mathematical entities that let you describe smooth surfaces. You may or may not learn about them in CISC 454. I'm not sure if there's time or if that's a topic of interest in that course. Right? And so it can easily do things like model flat surfaces and smoothly curved surfaces. Right? And so there's an example of building a house. Here's a little example of creating a shoe. Right? Again, you can see that the underlying model is just either triangles or, in this case, quadrilaterals of some kind. Right? In modern games, I guess the models, especially of the main character, might have tens of thousands or millions of triangles or polygons making up the model. Okay, so we don't need to watch this whole video. There are a lot of videos after all, so what's next? So that's Rhino. This is, oh wait, sorry, wrong one. Get rid of that. It's the same one again, I think. This is Autodesk. So Autodesk, for those of you who don't know, is one of the engineering companies. They used to be a strictly engineering company. So they are one of the companies where engineers would used to use their software to construct three-dimensional models, typically of stuff you're going to build. Right? And they also produce a bunch of other software related to that. So they produce software to do three-dimensional simulations. Which one did I want to show you here? This is photogrammetry. So instead of 3D modeling, the other way of obtaining, or one other way of obtaining a three-dimensional model is to take pictures of stuff in real life. Right? And so it turns out that if you take the pictures in a particular way, and if you take enough of them, you can reconstruct a three-dimensional model from the pictures themselves. So this is the problem called photogrammetry. Right, so that's the science of extracting 3D information from two-dimensional images. This is used all over the place in geography, science, gaming, obviously, or to produce the 3D assets for games. Right? Anywhere where you need to produce a three-dimensional model, this potentially can be used. So museums use this technique a lot, or use this family of techniques a lot to scan their artwork for archival purposes. This problem, the solutions to these problems come out of a field called computer vision, right? And there is a fourth-year computer vision course at Queen's. I don't know if it's offered every year or if it's even offered this year, right? But if you were interested in the photogrammetry problem and how you might solve it, that's where you would start. You would only start there. Trying to solve the actual problem has been the work of hundreds, if not thousands, of PhDs. And you can see here, just from Autodesk's description of this, it's used all over the place. Here you can see a person actually doing this process. So they've got this funny-looking device here. It's actually taking pictures of this thing here. And there's also this little pointing thing here that you might be able to see. That's a contact pointer, so you can actually touch it to the surface instead. It turns out that if you do this from enough, if you take enough pictures, or if you sample enough of the surface, you can recreate the surface. Right. I think there's actually a video here showing this in use, showing this technique in a game. Yes, Senua Hellblade. So Senua Hellblade is when did it come out? Last year or the year before, I think?
The game.
Yeah. Is it this year? Senua is brand new. There you go. So this is the creation of Senua. So I think it's a long video. We're not going to watch the whole thing. Come back, please.
To believe in our cast of characters by capturing the likeness of real actors and handcrafting costumes using traditional techniques, we'll achieve a level of realism that will further immerse you in our story. This is no simple task and has seen us push the boundaries of realism in video game characters, starting with Senua.
If you haven't seen Senua Hellblade 2 it's a beautiful looking game. Depressing as hell, but beautiful looking game. In order to create this game, this video shows you a little
My
bit
name
of
is
the
Dan
actual-
Crossland and I'm the character art director here at Ninja Theory. A character like Senua is comprised of many components such as anatomy scans, facial scans and rigs, physical costume creation, hair and makeup creation. Most elements are created physically so that it gives us a good blueprint and ground truth model that we can digitize later.
Much like film and TV, we're now creating real-life costumes that are scanned into the game. These are crafted with expert costume designers, using traditional materials and techniques accurate to the time period, to achieve a level of realism and detail that simply wouldn't be possible using purely digital techniques.
Right, so instead of an artist coming in and trying to recreate the cloth and the leather and the hair and the makeup on the in the three-dimensional assets, right? Another way to do this is to actually capture what these things look like using cameras, and then bring all of this information back into the three-dimensional images. So they actually hired an actress. This is the actress who plays
From
Senua.
the first game, I
We've got
didn't
makeup,
really feel
costume,
like I recognized
everything. So
myself
all
that
the things
much
you've seen on
because
television
I'm
and
wearing
movie
all this
production
face paint and
now shown
dreadlocks
in
and
video.
costume, and that's not how I walk around in real life. And also because the costume was modeled, it wasn't physically made, so I never actually got to wear it. Whereas this time around for Saga, we're actually physically making the costume, doing the hair, doing the makeup, so I'm getting way more attached to the character, and I can walk around in the costume, and like it's really, really cool.
The main reason to create a costume physically is so that we can scan the actor playing the character within the costume. We want the costume to fit the body correctly and have the weighting and compression in the right places, and we want to feel the density of those fabrics and how they fold and interact when in movement. We wanted the clothing for Senua to be functional and support her journey. As a player, you want to get behind her trials and key moments to believe in her struggle.
So that's what you actually see in the video.
Dan would give me an initial drawing. Then we would have a meeting about breaking it down, you know, so he usually just gives me sort of like one angle, you know, so sometimes I'm not aware of what's on the back, sides and stuff like this. So we'll break down what the costume is, how many pieces is in there. Then I'll go away and I make a toile, so that's just like a mock version, a starting point basically. Then we'll do one fitting. Things come to life when we start using the materials that he's after. Then from there I will I'll go straight into making the initial costume. We have one last fitting, and then from there it's like breakdown mode, so this is the most exciting bit before we go to scan. We'll break the costume down, meaning basically we're just making it look old and worn and sort of, you know, as that's been in a fight, or create these sort of like erosion lines, and also work on the colour a little bit more. In my studios, there are a lot of other artists, so I mean, to take the opportunity to work with other designers is sort of a given, really. I reached out to Weaver at my workshop called Francesca Miotti. She created the most beautiful woven. She was using hemp, jute and nettle. It's on the side panels of Mel's outfit, and it is just stunning. It's so beautiful to work with as well.
When creating Senua's hair for Hellblade 2, we did various shoots where we tried to use Mel's hair, but in the end we had to mat it up,
Oh, I just wanna
and
quickly jump
we
ahead
chose to add on an air
to
weave,
where
which
to how you
To
get
create
all
a
of this
digital
into
double
the-
character, we need two things: great data and amazing runtime systems to recreate the performance from the stage. The way we go about this is to use 4D scanning. You can think about 4D scanning as an extension of 3D scanning. 3D scanning involves taking a large number of photos of an actor, all taken simultaneously from a variety of angles.
Right, so you can see this, the setup they have here. Each one of these things here is a DSLR, so it's a pretty high-end digital camera. Right, they also have a bunch of lights, right, and these surround the, in this case, the actress or the actor, I suppose, however you want to call it, and they're taken from many, many, many different angles. Right? And this is a similar way that the movie, similar technique to how many movies and TV shows. That many
Using
movies
this
and TV
data,
shows use.
we can reconstruct a very accurate 3D model of the actor using a process called photogrammetry.
There you go.
Capturing 4D data involves the same process, but instead of photos, we use video. Once we have all this data, we can use it to create a set of blend shapes, a way of deforming the underlying mesh in a section of the face, and also a machine learning system that we can use at runtime to produce an incredibly realistic result. We use 3Lateral for this work because they're world leaders in creating real-time digital doubles, and we have a fantastic, long-standing relationship with them.
Our focus on crafting believability, as you've seen with Senua, will be extended to our principal cast in Senua's Saga, Hellblade 2. Doing so takes a lot.
So that's enough of that video. So this is the studio that produced this game is relatively small in terms of for the gaming industry. So that company is about 120 people. And so that's what goes into a quote-unquote small development studio. You can imagine what's happening in a larger development studio, right? Once you actually, so that previous example showed you one way of getting the appearance of materials into your world, right? You could take photographs of actual physical items, right? But that's not the only way to do it. In fact, it's probably not even the most common way to do it, right? Probably the more common way of doing this is with a process called texturing. And so in texturing, that's when you take your three-dimensional model, which has no color information attached to it, and you add actual color and...
When one model is the focus of your render and you want to show it close up, you need that model to look great.
Okay, so you see in the glasses, you can see it's got all sorts of nicks and chips in it, right? Those all arise from texturing. Those aren't physically part of the model of the lens itself, right? Those are applied after the fact with texturing. Oh, you can also, if you look very closely, you can see that the skin has a texture to it as well, right? Sort of looks like orange skin in this example here, right? Again, that's not actually modeled in the three-dimensional model itself, right? The underlying model is probably very coarse, so it's made up of fairly large triangles or squares, right? Instead, that appearance is applied after the fact with this.
Have materials and details that tell a story with every visible area carefully crafted. And that's when you need Adobe Substance 3D Painter. Painter gives you a set of advanced tools and techniques to craft and apply materials and details. You can paint by hand, making sure every fine point is to your liking, or you can work fast and efficiently by using automatic generators. You can also combine those methods to get the best of both worlds. You always work on a single specific 3D model. The textures you make are created specifically for this model. Ideally, it already has a UV layout, but...
Okay, UV. Who's heard of this term before with texturing? Okay, can you tell me what it means? All right, so the texturing problem basically boils down to this. So normally, normally a texture is just a 2D image, right? So you make a 2D image. In this case, I'm just going to do like a checkerboard pattern, right? That's a picture of your texture. So you can pull up like GIMP or Photoshop or something like that, make a digital picture of some kind, or you take a picture of something, right? You call that your texture. Right? Now the problem is this is just a two-dimensional plane, right? Just a two-dimensional image. You somehow have to wrap that around a three-dimensional object, right? So for example, if you wanted to wrap it to a sphere, right? Not a circle. How do I do a? So I want a sphere, right? You somehow have to wrap that two-dimensional shape onto this three-dimensional shape. And so the process that happens, it's a mathematical process that happens, right? Here you've got three-dimensional coordinates. Right, and here, your texture's in 2D, so it has 2D texture coordinates, right? And so, conventionally, the coordinates here are called U and V. That's U, that's V, right? Okay, so that's 2D. Now over here, you've got a 3D object, but it's made up of points, right? So, probably made up of points, right? And so somewhere on this sphere, there's this triangle that's sitting here. And so what you can do is you can say that at this point here, right, that has UV coordinates, say 0.3, 0.5. Right, so it's three-dimensional coordinates or whatever, some three-dimensional coordinate, right? But we're going to map that onto, so that's one, we're going to map it to here in the texture. And you take that whatever value is sitting here, so this is a color texture, you take that color and you apply it to that point there. That's the process called UV mapping. In the texturing software, you just see it called UV. So there'll be a control somewhere called UV. This is what they're talking about.
Substance Painter can also
If you want to learn about that, that's in CISC 454.
generate UVs for you.
Anyway. Oh, there it is, right there. So there it is. So there is the two-dimensional texture, right? So it exists as a picture, and you can see how it, you can sort of see how it maps onto this three-dimensional shape, right? What is the process that's used to map it? Well, it's complicated. It depends on how complicated the shape is, right? And so there's all sorts of techniques that are used to figure out how do I map this two-dimensional texture onto this three-dimensional object, right? And these tools will have, this software will have all sorts of tools to help you do this sort of thing.
And if you decide to change those UVs later, your texturing work will be transferred.
Does it change? Oh, that's
Substance
the point.
Painter lets you use information from your mesh before you start texturing.
Okay, who here has heard the term bake? Okay, what does it mean? So it means more than that. Right? So it's not just texturing. This term baking shows up everywhere. So the term baking shows up everywhere in 3D modeling. Well, not just 3D modeling. I mean, anything 3D, 2D modeling, it shows up all over the place. So when you bake something, all that means is that you compute something, probably that's expensive to compute, and you store it somewhere. Right? And so you store that information so that other things that rely on this information can use it later on. Typically, this is used for lighting in a game or a movie. So if you take graphics, right, you'll learn that when you go to actually compute what does this point look like when I go to render it on the screen, right, you have to repeat that process for every light that's in the scene. Right? And so if you have many, many lights, you have to basically render your scene many, many times, or at least you have to repeat the same computation many, many times. Right? If a light is fixed, right, there's no point in recomputing that information over and over and over again because you're always going to get the same result. Right? So if the light has a fixed location in the world, you can pre-compute the lighting for your scene for that one light, and you can store it in a texture, which you then can apply to your model, and you don't have to go through the process of computing lighting when you go to render. So that's an example of baking lighting information. You can bake all sorts of information into a texture and store it. I'm going to show you an example of that in just a second.
It's not required, but it quickly gives you a good base to start from. No need to paint and place those kinds of details by hand. Like Adobe Photoshop, Substance Painter uses a layer system. With layers, your ideas quickly become actual materials and details. You build up layers, determine placement on your mesh with masks, and blend them with other layers below. Layers and effects have parameters that can be tweaked, letting you iterate and adjust your materials easily.
Okay, let's look at the next example. So here's the baking process. So, okay. And so they talk about baking mesh maps here. And if you keep on going, bloop, 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 they actually tell you what can you actually bake into one of your textures, right? So you can bake the normal information into your texture, right? So what the heck is the normal information? Again, when you take computer graphics, you'll very quickly learn that when you have a three-dimensional surface, right, one of the important things that determines what a point on that object looks like is what direction in the world is the surface pointing at, right? And so on the edge of this circle, if I draw the perpendicular here, right, we say that the normal vector to the surface of that point, so that's going to be called n, right? It's typically a unit vector, so n hat, right? That tells you what direction that surface is oriented in the world, right? And every point will have its own normal vector. right? So it turns out the normal vector is one of the pieces of information that's needed when you go to do your lighting calculation and many other types of calculation, right? So collision detection and other things rely on this normal direction vector, right? If your object never moves, you can bake that onto the object in a texture, and it's much faster to look up that information in the texture than it is to try to recompute it from the surface itself, right? And you can bake all sorts of other stuff here. Ambient occlusion is effectively baking lighting. If your object never moves, you can do a lighting calculation ahead of time, store it in the texture. You don't have to recompute lighting at runtime, which is nice, right? And there's a bunch of other things as well. This is just an incomplete list. This is what 3D Painter lets you bake in. You can bake whatever information you want into a texture, right? And finally, if you want to learn a little bit more about UV mapping, there's the Wikipedia link for UV mapping, right? And that explains the texturing process. This is all covered in probably like 2 or 3 lectures in 454, where you only learn the very basics of how to do this. Motion capture. All right, so once you've got your 3D models, you have to make them move, right? If you have relatively simple models, making them move is not terribly hard. That can be done either programmatically or by hand, right? But if you want stuff to look real when you move, especially if it involves a human or an animal of some kind, it's very, very hard to have a programmer or some other person come along and say, so look, when you run, this is what all of your joints need to, this is what all the parts of the model have to look like. And so instead, we can use motion capture instead. But to do motion capture, it turns out you need a whole bunch of stuff. There's actually a very good...
Before we explain the motion captured mouse, who I've named
So this is actually a very, very good introductory video.
Moby Fitzsimmons, let's go to basics. We've all seen some photo like this one, with some poor actor in a weird outfit covered in dots, whether it's on the Hulk, Mark Ruffalo's Instagram, or Star Wars C-3PO's Anthony Daniels on his account. But where does that motion go? By focusing less on the actors and more on how it works, you can understand the real artistry behind motion capture. There are a few ways to capture motion. This is Rococo's SmartSuit Pro, and it uses inertial sensors. These broadcast the location of devices embedded inside the suit, kind of like how your phone knows which way it's turned. More common in high-end video games and movies, you'll see optical tracking of markers, in which a camera is learning where parts of a person's body are by looking for high-contrast areas. Jimmy Corvan directed business development for motion capture studio House of Moves for about 10 years. They've worked on everything from the Injustice series to Mortal Kombat to Marvel movies to Barbie's vlog.
Comment, like, and subscribe so you can get the latest and greatest Barbie vlogs and more.
Is it more common in high-end stuff like what y'all are doing? Is that pretty much always going to be optical thing rather than like a sensor?
For the foreseeable future, and I'm sure there's somebody at one of the inertial companies that will correct me on this, but in all of our testing and everything that we've found, optical motion capture is sub-millimeter accurate.
These suits...
Right, so what they're saying there is that they can, if you see each one of those little silver dots, it's possible to measure the 3-dimensional location of that dot to within sub-millimeter accuracy. If you know anybody who's taken the computer-aided surgery course in 3rd year, or if you've taken it yourself, you would have seen one of the tracking systems that are used for this sort of thing. So in many forms of computer-aided surgery, they're using the exact same technology. They've got these little markers attached to the surgical tools and to the patient, and they're able to track the movement of the tools and the patients in real time. Right? The technology that's used for video games, movies, television, same principle, different implementation.
Don't have any sensors at all. They're basically fashion made to be seen really clearly.
I will always get the question, how hard are they? How do you get the technology in the balls? And I'm like, well, you can squeeze them. Like, there's just retroreflective tape on.
Okay, so these shiny balls, that's all they are. They're literally shiny balls. They're plastic or ceramic, and they're coated with a metallic coating The metallic coating is called retroreflective. All that means is that when light hits the surface, it bounces back in the direction that it hit it in. I think he's going to explain more.
The outside of little squishy balls.
The footage shot with suits on is fed through software that interprets what the camera sees before artists review it. If you look at Mark Ruffalo's tweet of him, Tom Holland, and Don Cheadle on Avengers Endgame, you can see how additional symbols allow software to know more about the location of the suit on the performer. Even if one symbol is dark or out of focus, the software can figure out what's going on thanks to the pattern.
The first step in the cleanup process is somebody goes through and makes sure that you can see every one of those dots in every frame of the shot. It sounds tedious because it is.
So imagine being that person, right? This is filmed at 24, 30, 60 frames per second, right? Someone has to go through frame by frame, look at all the balls in the picture and make sure the software has identified them correctly.
So all the markers have a different name, and somebody's job is going through making sure you can see each marker in every single frame and that each marker is properly named. That process is called tracking and labeling.
This can be augmented with facial capture like this.
Oh, sorry, that was a good picture.
It's called tracking and labeling.
This can be augmented.
Okay, so this is a similar idea, different implementation. So here they've got dots on the actor's face. These dots are being captured by a regular camera, right? And they're using the same idea. So if you know where that dot is on the three-dimensional model, right? You can warp what's happening here onto the three-dimensional model, right? So this is an example of a registration problem, right? I need to match that point to the corresponding point on the model, right? And you need to do this for every point. Registration problem shows up all over the place, shows up computer-aided surgery, shows up in these motion tracking applications, and in many, many, many other places.
With facial capture like this, a range of motion capture gloves, and even the ability to label and motion track objects. For hobbyists, there's
back there.
Even the ability to label.
Okay. So if you know that many factories these days are fully automated, so in other words, there are factories that exist where there are no people in them. It's just a bunch of robots moving around. In these factories, typically walls, shelves, objects are labeled with these funny shapes. That's so that cameras that are attached to the robots or when I say robot, I mean like a lift truck, perhaps a robot, right? Some automated machinery can actually identify where this thing is in the world, right? And so they use a bunch of unique shapes. This is not a particularly accurate example, right? And that lets the whatever's moving around in the world figure out, okay, so item or box number 4, right, is right here, right? Item number 12 is up on the shelf over there. The shelves are here, and so on and so on and so forth. So in these automated factories, they're all really brightly lit. Everything moving around's got cameras on it, and it's looking for these distinct symbols.
And motion track objects. For hobbyists, there's stuff like Moby Fitzsimmons. His form comes from a free-to-download mocap-ready website. I captured his movements using AI called Plask that just figured out the motion without...
Okay, and so you can see here that he's actually doing motion capture with just a single camera, which is pretty new. So the way this all works is it all works with a neural network of some kind. So the neural network has the model of a human being, and it's able to, from a single video stream, guess at the motion that's occurring just using the video information itself from a single video camera. So this is a relatively new-ish technology made possible by deep learning.
Without any dots or sensors. These methods can vary wildly in cost and quality, but the output is actually...
Keyword there is quality, right? You don't get sub-millimeter accuracy with the...
similar. It's bones. This structure is the basic output of most motion captures. No cloth, no muscle, no...
Okay, so notice here that you don't have a three-dimensional model. What you have is the skeleton. Instead, attaching the skeleton to the three-dimensional model is called rigging, right? And rigging is the process of determining how the thing moves given its skeleton, right? There are if you're doing all of this using three-dimensional modeling, there's going to be a rigging artist who has to go in and insert the skeleton into the object.
Hair, just what the software calculates as the skeleton. Each dot here is a joint, while the longer shapes are bones.
Those are
In
where
this
the markers are
example,
typically
they're
attached,
my bones,
right?
soon
The
to be
markers are
Moby's.
typically attached to the joint.
These bones are given a hierarchy, so if the top of your arm rotates, the lower part usually will too. These subtle variations can convey a lot of movement. These numbers represent the rotation of a single elbow joint. Watch how they change as the elbow moves during the animation.
We are trying to figure out exactly where the skeleton exists, because that's what we're really capturing is your skeleton moving. We aren't actually capturing the flesh on top. We've gotten very, very close, but it is not perfect. If the bone lengths are just slightly shorter or slightly longer than even something as simple as like clapping, like if I were to do this, it might end up that they go through each other like this because the bone lengths are different. That's where animators come in. There's a lot of that fixing, and you end up seeing it in postures. There's a very popular phrase in the mocap space called monkey butt, and that is the hips kind of jut back a little bit, and it kind of looks like they look like they have a monkey butt. And so an
Now you can tell your friends that they have monkey butt.
animator will need to go through, push the hips back forward, kind of undo that work.
This outfit provides a clue to why motion capture is harder than it looks after the data is cleaned. The Hulk is significantly larger than Mark Ruffalo. VFX artists take the time to make Taika Waititi's capture fit the body of Korg, but you can see what goes wrong without extra work. See how Moby's hands run into his face here? That's not a problem when I do it because I don't have a head like Moby's. The same goes for position in space. See how his feet wobble around? This is part of why you don't see tracking images on the actor modeling for Groot, a tall, talking tree, or actor Sean Gunn, who stands in for Rocket Raccoon. These figures, and even motion captured figures, are too difficult to graft on human motion, so the people are just used for reference.
Even if you're not using, all of the data specifically, having the timing created by the actor or performer is really, really helpful. A lot of people, like myself included, I talk with my hands. And if an animator tried to animate me talking with my hands, they'd get the timing wrong.
Look at this side-by-side of Hulk and Mark Ruffalo. Ruffalo gives a great performance that you can really see, but look at Hulk's shoulder size and the cloth and the space his hands take up. You can even see in this clip how his right hand has been tweaked completely after the capture.
Enough of that. So all of that tweaking, that comes in after the fact, right? So there's artists who have to go in, tweak the 3D modeling to get a more believable or a better result, right? So even if you have motion capture available to you, there's still extra work to do after the fact. I don't think I'm going to play that link there. That's the link there that shows you the actor from Black Myth Wukong and doing some motion capture there. And so if you wonder how they did these crazy animations that you get in this game, it's all motion capture, right? And then cleaned up afterwards by another artist. Okay, terrain generation. So there's a lot of games now that use that are open world. They have huge, realistic-looking geography, right? Modeling that sort of stuff. You don't want to model that sort of stuff by hand, right? The world's just too big. And so there's software specifically made to do this sort of thing. TerraGen is just one example of this type of software. Okay. Somewhere there is so what's TerraGen? So TerraGen's a solution for building, rendering, and animating realistic natural environments. Somewhere there's a video. What's new? Sorry, I guess I should have loaded this before we came in. All right, I guess it's not. It's not the end of the world if you don't see the video that's associated with this. But there is a. Where did it go? Hang on, sorry. Now it's bugging me. I think there's a. Come on, Wi-Fi. There's supposed to be a link here, if I remember correctly now. All right. If I can find that link, I'll put it in the slide. There is a link, though, to a video for this. Quest editor, so dialogue and quest editor, so certain types of games typically involve the player interacting with non-playing characters in the game. And often that involves dialogue, and often the dialogue affects what happens later in the game. Right? Usually in these types of games there are quests, so there's a sequence of events or actions that the player must complete in order to complete the quest. And so getting this right is hard to do, especially if you're just programming it on your own. Right? There's many games that have quests that are broken, right? Bugged out quests that the player can't complete because something's gone wrong in the quest line. There's software to help you manage your quests as well. You can click on that and take a little view of that. Finally, this one is not necessarily related to video games, but it is used.
MassMotion version 11 is a major upgrade of the world.
It's used a lot in the real world by architects and engineers to model how do crowds move in places, right? And so architects and engineers will use this to model model buildings, roads, bridges, anywhere where there might be people moving around.
Its most flexible human movement package.
Flow of traffic.
New features allow users to better communicate and model results to stakeholders, and a new toolset makes automation and customization significantly more accessible. Moving through the steps of creating, simulating, analyzing, and revising a space, MassMotion can be used to model a wide variety of environments and project types, providing insight into how designs and operations can be optimized from a human perspective. New agent avatars allow enhanced playback of simulations, with users able to show multiple genders and better represent different person types. In addition, agent height scaling adds more value to first-person perspectives to convey sightlines and user experience. Dynamic fly-through cameras can bring MassMotion models to life in new ways, allowing users to present their models with much greater flexibility. The new camera object contains an easy-to-use system to quickly generate fly-through videos and has the flexibility to create complex paths for advanced users. The new billboard object allows increased feedback throughout the scene, easily add text and signage to models. Users can also display key analytics such as the number of people in a queue or counting down time until the next vehicle arrival. Automation has become much more accessible in MassMotion thanks to the new script object. The script object can be used to automate and customize all aspects of the modeling process, further establishing MassMotion as the most...
So there's an example of crowd modeling, not in a video game. So in video games, though, you do see examples of, simplified examples of what this is doing. Right? So if you play a game like There Are Billions or something like that, one of these games that has lots and lots and lots and lots of non-playing characters running around, they are effectively running a crowd simulation of some kind. Okay, so you can see that there is not much time left in the lecture. All right, so you can see that there are many different groups of people working on the game, right? It turns out that the amount of data that these people are working with is enormous, right? So if you motion capture something, you're basically taking video, right? Not just one video, but possibly video from many cameras. Right? And so you capture gigabytes or terabytes of data, right? And so somehow you have to get this data around to people, right? And then the game itself, especially in one of these modern video games, there might be millions of assets, right? Each with its own underlying model and own underlying textures, right? And so the amount of data that makes up a modern video game is enormous, right? And the people who are working on this, they all need access to it. And so how do we make sure that all of the different tools can actually use the data that's being produced by other tools, right? And so it turns out the tool creators all have to agree on basically either agree or document how they're storing their data, right? So that other tools can then import their data, right? And so for example, Maya and Unity's FBX, those are both three-dimensional modeling formats, right? It would be nice if they were interchangeable. So can Maya read Unity's FBX? Yes. Can Unity read Maya's export format? Yes. Right? And so it's quite important that the standards that are being used are open, or at least documented well. Right? Notice Microsoft's not involved in any of this. Okay. Finally, because there's so much data kicking around, it's important that that data be carefully managed. right? So you're not using Git for this, right? No one's uploading all this stuff to GitHub. There's like gigabytes or terabytes of data. There's actually specialized software that deals with repositories for this type of work, right? So Plastic SCM is one of these repositories. If you click that link there, it actually takes you to a demo of using Plastic SCM in the video game industry, right? And so hopefully that lecture is giving you just a little sample of what's actually going on in a modern AAA game, right? Obviously, we can't talk about even the tiniest fraction of what's happening here, right? You'd have to take, I don't know, hundreds of university courses to learn everything that's going on in a modern video game. So what little bit of information I can convey to you, I will in the rest of this course, right? And so on Monday or Tuesday, whenever we meet, Wednesday, when we meet next, we'll start the actual technical content of the course. All right, thanks for coming out, everybody. See you next week.